Welcome. This video gives an overview of a high school learning project that uses industry-level engineering software to support student success with next-generation science standards. This project was made possible by a partnership between ANSYS and the School of Industrial Design, Engineering, and Arts in Tacoma, Washington. The objectives include engaging students with project-based learning and a real-world application of design thinking. This is accomplished through the use of 3D modeling and physics simulation software created by ANSYS and traditional metal fabrication tools found in many high schools. Throughout this project, students are provided with chances to master many of the next-generation science standards in physical science and engineering. The most thoroughly addressed NGS standards are in engineering, particularly number 4, which deals with computer model and simulation. Before ANSYS, I struggled to find software that was meaningful, robust, and flexible. The educational and industry-level products provided by ANSYS make this standard easy to achieve and engaging for students. Additionally, since this project deals with thermodynamics and energy transfer, there are a number of great learning opportunities for NGS standards in the physical science domain, such as these three, and particularly Standard 4. After identifying the learning objectives, the next step in backwards design is determining how to guide students to them. My chosen model is project-based learning, as summarized in this gold standard definition created by Buck Institute. Their website provides additional resources for those wishing to know more. To structure the project for students, I use a design thinking model created by Stanford School of Design, or D-School. This simplified and linear model allows students to easily understand what they are doing at any point in the project and how it connects to the larger goal. For my class, each step of the project had these specific activities attached to them. In the following slides, I will walk through each part. The project begins with students empathizing about the needs of our client, who are an imaginary kitchen gadget supplier. After noticing that hot drinks cool faster when a spoon is left in them, they recognized an opportunity for a new marketable product. They've requested that we provide prototypes of products that accomplish this same task but more effectively than a spoon. I created a one-page summary of the features these products should contain, including specific constraints on size and effectiveness. Since some criteria required balanced trade-offs, this document also helps students determine which variables can be adjusted during design optimization. This activity is followed by a quick round of hand-drawn sketches. The defining process continues with an exploration of the properties of our building material, in this case aluminum rods and bars. Later in the prototyping stage, where students analyze thermal transfer in their design using ANSYS DiscoveryLive, their results will only be as accurate as the input parameters. In this case, those parameters include thermal conductivity and specific heat. Unfortunately, thermal conductivity is a challenging property to measure experimentally with the resources of a high school. So instead, I guide students through the process of interpreting spec sheets that are typically provided by metal suppliers. Specific heat, on the other hand, is something that can be determined with fair accuracy in a high school lab and only requires the measurement of temperature and mass. First, a test sample of known mass is raised to 100 degrees Celsius by means of a hot water bath. The sample is then placed in a well-insulated cup of room temperature water with a known mass. Once this system reaches thermal equilibrium, the final temperature is measured. If the cup is well insulated, most of the energy gained by the water is the energy lost by the sample. With this knowledge, students apply the equation on this slide to solve for the last unknown, the specific heat of the sample. With the project now well defined, students turn towards the ANSYS software. They get an introduction to DiscoveryLive and its underlying space claim environment by creating a 3D model of their hand-drawn sketch. In other videos, I will provide support of how to guide students through this process. Next, students are guided through the process of creating a thermal solution for the design. For the analysis, the rod, which is assumed to be in a boiling hot drink, is held at 100 degrees Celsius. The structure on top is allowed to transfer heat via convection to the surrounding air. The temperature of the air and rate of convection can both be adjusted if desired, but since students are just comparing the effectiveness of different designs and not trying to make quantitative predictions, this isn't necessary. To track the amount of heat flow out of the upper structure, a probe can be placed on it after selecting all the faces. Since heat is flowing out in all directions, it's important to have students adjust how the calculation is being made, as shown in this image. By default, the probe will only look at the X, Y, or Z direction, so they should set it to sum. After this, when students make adjustments to their geometry, they will be able to see how each design change either increases or decreases the heat transfer. In this example, I made the valleys between the fins a little deeper, which increased the heat transfer significantly. Lastly, students edit the material library so that the default values of thermal conductivity and specific heat more accurately match those they found in their lab investigations and research. With the material properties now adjusted and the heat transfer through the upper face serving as a figure of merit, students begin to use the full power of DiscoveryLive by making numerous and rapid design revisions. With each revision, they are trying to reach the optimization goal of increasing how effectively heat is transferred while maintaining manufacturability. Once students land on a design that meets all the requirements of the client, they move to physical fabrication. As a construction material, aluminum is relatively inexpensive, so I have every student fabricate their own product. Tools that we use include mills, lathes, drill presses, taps, and dies. These are tools that are commonly found in any high school metal shop. Upon completion of a physical prototype, students move on to testing and evaluation. The client requested that the prototype be at least 10% more effective at cooling a hot drink relative to a control cup with no heatsink. Students gathered this data by applying computer science skills to build and program a microcontroller circuit. The data gathered by this device is analyzed in Excel and included in a final report.